All right, so now we come to a few slides which really you should not worry about too much. We're starting to look at these two distributions that we introduced, the binomial distribution and the Poisson distribution, and we'll start with the binomial distribution. And the binomial distribution is basically the coin tossing distribution. Um, you have a random variable which is heads with a certain probability mu, and tails for a different probability 1 minus mu. The total probability has to be 1, and then we're counting up the number of heads or the number of tails. In the application for histogramming, heads means the event lies in a bin, tails means it lies outside the bin. If we have lots of bins and lots of events, then the probability for any one bin which is looking at one bin here, that one event lies in that bin is small. So this number mu is small, the number 1 minus mu is big. So these are not normal coins with equal probability of heads and tails. These are coins where the probability of heads is very low. If you then calculate the mean value of this random variable is x, of x, that's mu, and the standard deviation is 1 minus mu into mu, which for mu small is approximately mu. So this 1 minus mu, which is actually relevant if you have, has to be included when you have probabilities mu which are quite big. That's actually what you would have in a presidential election, where roughly mu is about around 0.5. People maybe only vote for 2 or 3 possibilities, person number 1, person number 2, or none of the above. So if you look at any one bin, the probability actually mu is around 0.5, and 1 minus mu is also 0.5. So this effect, 1 minus mu factor, is important for cases with small numbers of bins, but it is not important for the cases we're doing here for physics when we have lots of bins. So that's what it says here. Mu is tiny for our applications, and we have the basic result that the average of the standard average of the random variables equal to its so-called variance, which is the square of the standard deviation, and they're equal to the same thing. So its standard deviation is the square root of the variance, which is then the square root of the mean. So that's our basic result. If we observe n events in our bin, the error is always square root of n. And you formally do that by forming this, make a formal definition of x to be 1 if you're in the bin, 0 if you're not in the bin. Then the total number of events in the bin is the sum of the x's over all the random variables, and then you can see that the mean and the standard deviation, the mean is always the square of the standard deviation. Basic rule, and as I keep stressing, a very important rule. Here is just an example of where the CMS experiment also saw the Higgs. It's a different final state, but this is an example of a histogram with quite a lot of structure. There's a peak here, and a big peak here, and you have to do a physics analysis to decide which peaks is interesting. This one here turns out belongs to the Higgs. It's not a terribly significant peak. The background's around 7, and the signal's around 18, and the square root of 18 is a little over 4, so 7 is a couple of standard deviations. So this is not significant. And you have to do two things. You have to do some physics to decide what these peaks are. In this case, you found that there were particular final states, which are very rare, but not the Higgs, and also final states involving known particles. And you have to do so-called Monte Carlo calculations, I mentioned at the end, to see that these peaks here and here do not correspond to anything particularly interesting. So that says that All of these analyses require careful making of models and putting that model into your detailed analysis. Here is actually the same type of final state, the two-photon final state, but now from the CMS experiment, not the Atlas experiment. And we see again this peak at 126. Actually, it's a little above 126. So I'm not quite certain what that means. Maybe it's not. No, I'm wrong. It's actually about 126. It's not above. That's a mistake. I misread the graph. So this peak here is actually more like 125. But at this time, one of the reasons they did 2 experiments, each with 3,000 people, was when you get signals like this, you really need to make certain it's A, not a statistical fluctuation, and B, not some artifact of the apparatus. You address both by running 2 experiments. Thereby, you get twice the data, but you get totally different possible experimental biases in each case, because though the experiments have the same goal, they differ tremendously in detail, and therefore very unlikely to have the same systematic errors. This slide here just makes a very general comment, which we'll see in the homework. Then we have always a signal. That's this thing here. Sorry, the signal is this thing here. And we have the background, which is this thing here. And then at one stage, we have some background events and some signal events. Now, if we were just viewing the signal, then the error in the signal is the square root of n sub s, whereas n sub s is the number of signal events. It's not so difficult to get, say, 5 standard deviations. That just means you need 25 signal events, and the square root of 25 is 5. And so if you see 25 and that's it, then you've got a 5 standard deviation effect. However, what you really see is your signal on top of a background, which was in the cases we looked at, thousands of events. And the error is not the square root of the number of signal events, it's the square root of this number of signal plus the number of background events. And you need to make certain that the square root of signal plus background is smaller than the signal, because otherwise it was very hard to identify these bumps. As I've said many times, any analysis like this has statistical errors, which we've just discussed, and also systematic errors, which depend on the model-dependent uncertainties, which need detailed domain knowledge. If you're doing the presidential election, you need to be an expert on polling to know what the systematic error is in your choice of people to call up. If I'm doing physics, I need to know the quality of the theoretical models to estimate how good the background was, and put that into my analysis of the systematic error. We would also use so-called Monte Carlo to study which we'll mention later, to study the apparatus. And we would get systematic errors if we didn't study the apparatus correctly, because you can never find everything out about an apparatus, because you're not going to run events through the apparatus which are exactly the same as the observed events, and there may be some feature of the response of the detector which you just didn't model correctly, and therefore you will get a misestimation of its effect. So whenever you see error bars on at least a modern, sophisticated experiment, they usually correspond to systematic and statistical errors.